Yeah, I'll try to keep it short anyways. So yeah, I'm gonna tell you about a small library that I wrote that has some nice like dependency types techniques basically. So if you want to write something also. It's written in Idris too rather than Acta because I'm doing a lot of dirty stuff and Idris gives me the ability to do that and then hide it all away so that the interface is hopefully safe. Right, so we'll start with session types. So we want to describe some small protocols. I'm flashing the grammar at you, but it doesn't really matter. We have fixed points, sends, receives, offers, and selections. Basically, to get an intuition for this, so if you're a server and you're offering the adder protocol, where you're going to get a bunch of numbers from someone else and eventually return the sum, this looks something like this. So in terms of protocols, at the top, we have this thing, which is the protocol in the initial states. It's telling you with the ampersand that you're offering two possible moves for your clients. The client can either decide to eval the current sum and you will send back a natural number and then stop, or they could, and then stop, okay? Or you could pick the other branch and then you're responsible for sending an additional argument to the server. We will then add it to its running total, and you will end up back at the initial step. So that's what the fixed point is giving you, right? It's this ability to loop inside the state machine. And here, it's a greater fixed point because you're the server, so you're not in charge of deciding when to stop. The other person is feeding you numbers, and then eventually they are responsible for deciding to get the sum. And then you can build something a bit more complicated. So now you're repeatedly offering this small protocol. So again, you're starting in the ready state. You're offering two possible moves. You could just, the client could just not want to sum anything and be done with it. Or they could say, okay, I'd like to sum something. So just for, to make things slightly different, now you start by greeting them, and then you're entering this loop that we saw earlier. So this time, instead of finishing when you're, when the client is calling eval, you're going back to the ready state so that you're willing to go through another round of these things. So again, you have the original loop that we were seeing before, and you have a bigger one, which is repeatedly offering this behavior. So that's what the nesting gives you, the ability to basically have these sorts of machines described. All right, so then we want to write protocol respecting programs. I'm not showing you the type because it's disgusting. You can go look on GitHub if you want to see it. But the idea is that, so we have this abstract machine that's describing the behavior of the protocol, and then we're making some various moves. So you can see here that I'm reusing the same name for the channel all over the place. So this should be a hint that we're going to use some kind of linearity or uniqueness to ensure that the channel is properly stepped after each move in the protocol. But we can go through this slowly. So I told you that at the beginning we had this greater fixed point, so we need to actually enter it to be able to expose the choice we're offering. And then we are making an offer, it's here, which means that we're going to get a decision from our client telling us whether they want to take the left branch or the right branch. If they take the first branch, we're in the eval, which means we are sending back the accumulator in this instance where we've accumulated the sum. And then we are recursively jumping back to the ready state, which is exactly what we saw in the big finite state machine we had before. And if we're picking the other branch, well, if the client is picking the other branch, then we are waiting for an additional argument, and we keep and we return this time to the init state. So I called it adder rather than init, but whatever. And so, oops, yeah. So here we jump back in the protocol using rec, and then we call ourselves recursively because we are now in such a state in the protocol that the recursive call will actually type check with the extra arguments. All right. So in Idris, we have typed communications. We have a notion of channel, which is typed. The problem here for us is that it's taking a unique type, so A, that you pick when you create the channel, and then you can exchange messages using this A. So here I'm receiving a value, and here I'm sending one. You can see that this channel is also never consumed or anything. So if you have the idea of building a protocol that will evolve through time, that basically you need to build it on top of this very basic machinery that only gives you channels for one type of messages. So the first thing to do, okay, so this is picking one type at the beginning and sticking with it. There's no protocol, no nothing on top. So the first thing to do is to think about the sort of message types you want to send. And because you know the protocol statically, you can actually compute all of the message types you might need throughout the execution. And then you can form a big union of types in which you will be able to inject all of the separate messages that you have. So what this gadget is doing, it's telling you, well, if you have a list of A's that are a notion of codes for types, they don't have to be types themselves, and you know how to turn A's into types, then we're forming this big union thing that, so there's a bit of an encoding artifact here, but the moral of the story is that you can basically store an element of type T for any T that is somewhere in T's. And this is somewhat related to what Wayne was talking about in the previous days, right? So we don't want to be storing slow de Bruijn indices, basically describing where in T's the T is present. So what we have is a NAT, which in Idris will be compiled to a GMP style integer. And then we just have an erased proof that this NAT is pointing to T inside T's. So this is the representation we use in Idris, in the Idris compiler itself, in the internal representation of well-scoped syntax. Yep.
Why not take a list type directly? Why don't you take a list type directly?
Because this is more general. So in this case, I only need the list type because this is library code, actually, rather than my code. It's the most general it could be. All right. And then, as I said, because we know the protocol ahead of time, I haven't defined the session type yet, but it doesn't matter. We can define these functions that are computing the things we are going to need to exchange over the wire. And so then we have this big, unique type of messages we can exchange, which means we can use Idris's notion of channels to talk to someone else whilst respecting our protocol. All right. And then last thing, the stateful protocols. So the other tricky thing is that when we're communicating, the protocol is stepping through, and so we're making destructive updates on the channel, right? So what we're going to do, because Idris doesn't have a notion of uniqueness typing, is to abuse linearity to encode uniqueness. So this is me promising you that the primitives I give you in the library are ensuring uniqueness, and as a consequence, everything should be safe. But it would be nice to have unique types eventually, just like we used to in Idris 1. And why am I not using Idris 1? Well, because I want erasure, and it's only in Idris 2, so you have to pick your poison, basically. I'm not unfolding fixed points by substitutions, and this is exactly what Connor was saying or 2 days ago, maybe, about putting the toothpaste back in the tube, right? If you substitute, when you enter a fixed point, you substitute the code for the fixed point for the variable pointing back to it, then you've lost the structure, and your functions computing the list of sent and received messages is just getting confused about all of these unfoldings. And suddenly your list is growing with extra types at the back, and it's a nightmare. You don't want to do that. And of course, because we're progressing through the state machine, describing the protocol, but we have a single type of messages that we can exchange, talking about all of the potential types that are being exchanged. We need to record where we are in the machine so that we can translate the current message we want to send back into the big union type that we defined at the beginning. So this is the syntax of session types, or rather the interesting bit. So I have two kinds. I have the largest and the smallest fixed points. They're using names because I'm thinking of users. I'm not being nasty. When you introduce a fixed point, what happens in the body basically is that you're pushing this kind onto the scope. So it's telling you that you have a new variable in scope. This is just well scope by construction sort of syntaxes. And then you have this rec constructor telling you that if you have a kind somewhere in the scope, you have a session of that scope. So you're going to jump back to that thing. And here, I'm not using a name. I'm using something that encodes this invariant that's KD somewhere ends, because I haven't quite fully thought of users. So this is nice for me, but not for the people actually writing the sessions. And then you have your usual stuff: send, receives, and offers, selects, etc. The norm gadget here is to ensure that you're never building empty protocols. We want to be able to ensure that if you have a protocol, we know that at some point you're going to make some progress. You're not just going to loop infinitely in the protocol. So as I said, we're not substituting anything. We are building an environment of codes for the bodies of the various fixed points we've encountered. So that's a telescopic thing. And then this is the big type of channels. Maybe I don't have time to explain it, but basically you can see that you're currently at some point in a session with an environment explaining how you can interpret all of the fixed points you've gone under. And you're storing an erased original session, which is the one you started from, telling you the types of messages you're exchanging. And then you have a gadget, which is a bit like a zipper, but we don't care about recording the loops in the finite state machine, because it's just taking us back to where we are. So it's a delooped zipper, basically. And then we actually have the channels we're using to communicate. Okay, and then we can define the usual thing you'd expect that you can use to program. What's next? So because of all of these fixed points, I couldn't get everything erased quite yet. It would require some nasty invariants, so I just decided to keep the context unerased, which means there's a small runtime overhead where we're computing offsets that we shouldn't have to compute at runtime. There's a bit of ergonomics. As I said, this focus thing makes the types really big, because you're talking about where you are in this list of bodies describing the fixed points. So there's a lot of repetition in the types, but this could be magicked away with a bit of computation. And finally, totality checking. At the moment, when you're the server, there's nothing allowing you to perform co-recursive calls in a guarded manner that is guaranteed to be productive. But because of the shape of the protocols, we should be able to trick Idris into accepting the fact that when you're going under a greatest fixed points, you have the right to call yourself recursively. And that's it for me.